He's going to talk about dynamics of disorder, quantum interacting systems, distribution functions, and autocorrelated disorder. Please.
Okay. First, let me thank you to the organizers for having me, especially to Dario for letting me present my work. Yes, I'm from Puebla, Mexico, so I'm going to talk to you about the dynamics of disordered quantum interactive systems, something that Lea already told you during the morning, but I'm going to talk about some specific aspects of the dynamics. In particular, I'm going to present results about the distribution functions at late times of different observables under the evolution, let's say the evolution under disordered systems or disordered Hamiltonian. And we are going to see what happens with the dynamics when the disorder that is included in the system is autocorrelated, some kind of specific correlations. So this work was done in collaboration with Lea Santos, which is here, you know very well. He was born here in Sao Paulo, and so on, do you know this history? And my former PhD student, Isaías Vallejo, which is now doing a postdoc with Lea. And my talk will be based in these three papers. In particular, the first part is based in these two papers, and the last part, a very brief part, is in this other paper. So this is the contents of my talk. First, I'm going to introduce quickly the time evolution. Which is the image that we have to study the time evolution of a quantum many-body system. I'm going to define the quantities that we are going to study. Then I'm going to introduce the model, which is actually the XXC model with on-site disorder. Then I'm going to talk about some static properties like the energy level distribution, and we are going to see level repulsion, for example, and when there is no level repulsion. And then we are going to remind the central limit theorem, which is related to some probability distribution functions. The results that we are going to see is that, for example, this is one of two of the observables of the quantities that we're going to study. This is the survival probability. This is the so-called spectral form factor, and we are going to see that at that time, the distribution, when the system is in an ergodic phase or chaotic phase, the distribution is exponential. And for the correlation functions, the distribution is Gaussian. Then I'm going to present you the results of the effects of the correlated disorder in the dynamics of the system. So this is the picture that we have in mind for the time evolution. We have time zero, we have an initial state. I mean, we prepare the system in an eigenstate of this H0. Then we suddenly turn up some interactions or perturbations represented by this B, and we evolve the system. No? I mean, we take out of equilibrium the system. This is a typical picture of the time evolution of a generic observable, which is given by this prescription. I mean, this is like what Thomas called the theory of everything. Yeah, right, something like that. Yeah, because this is only quantum mechanics, right? There's nothing else. There is no a specific system involved here. It's just a quantum system with these eigenstates, for example, and these eigenvalues. Then if you take one initial state, this initial state is evolved by this unitary operator, where this is the Hamiltonian dictated or generating the evolution. You can expand this evolved initial state in terms of the eigenvalues of the system and the eigenstates of the system, the energy eigenstates, with these components, the projections of the initial state into the energy eigenstates. So the time evolution of a generic observable is given by this expression. For a long time, let's say formally when the time goes to infinity, you get this, if the system doesn't have many degeneracies, then you have this quantity, which is called the diagonal ensemble, which is represented by this straight line here. So as I told you, this is the typical evolution of a decaying observable with time. You have a transient behavior first, then you have saturation at this value, which is, again, this is the diagonal ensemble. So this is the approach that we have for the time evolution. Then we have different observables that we can study for many body systems. They are of interest in, for example, in modern quantum platforms. I mean, for example, quantum or cold atoms or ion traps. Then one is, for example, you have this, you define this operator, which is the projector of the initial state. Then you can have the survival probability written in this way. When you have this for short time, you have this for large time. I mean, if there are not many degeneracies, then this quantity arrives to this prediction, which is called is known as the inverse participation ratio, which is a measure of the degree of localization of a given initial state in this basis. Then if you have, for example, one initial state that is extended in a certain basis, completely extended, then you recover from this expression, you recover what is called the spectral form factor. Other observables that you can study, this is the spin autocorrelation function, and this is the spin-spin connected correlation function also. So I'm going to present you some results on these observables, these quantities. The model that I'm going to present is this one. This is a one-dimensional system of L spin-half particles interacting between parts. This is a term which represents couplings. This is an Ising-like interaction, and this is an external field, let's say, in the z direction. We consider closed boundary conditions or periodic boundary conditions. This delta is known as an isotropy parameter, and we are going to fix this delta equal to 1 in the sense that this is known as the XXC model or the XXX model. And this is, again, this is an external field. This HK is the amplitude of this external field. The S is written in terms of the spin-half Pauli matrices. In this way, we consider units in which H bar is 1. What else? HK are random numbers from a uniform distribution with this support, minus H to H. H is the disorder strength. So if we have H small, we talk about a small disorder. If we have H large, let's say larger than this, than one in this case, then we talk about a large or strong disorder strength. So since these numbers are random numbers, they can be uncorrelated, meaning this, I mean, if we have the average of this product, we can separate in terms of the product of the average, and they can be also correlated. We cannot do this separation. This is in general. Then this Hamiltonian conserves this quantity, which is the magnetization in the z direction. In this way, we can separate the Hilbert space in different sectors, symmetry sectors with different values of total magnetization. Since we are going to do statistics, let's say with the eigenvalues, with eigenstates, then we are interested in the largest one, which is the one with zero magnetization, total magnetization in the z direction with this dimension. Now consider the total dimension of Hilbert space of this system is 2 to the L. Then in this way, if we restrict ourselves to this subspace, we gain this advantage, which is we reduce the dimension of the space in which we work in this one. So this is a well-known model. It's a paradigmatic model for many body localization. So I'm going to work with this model. First, what we do is an example of level statistics, which is the level spacing distribution. I mean, this is the probability distribution function of the space, the consecutive spacing between adjacent energy levels. The first thing that we do is to order, in this way, the energy eigenvalues. Then we compute the spacings, and we draw the histogram of these consecutive spacings. And here is an example, for example, of these level spacings. The histograms are numerical results for different values of H, the disorder strength. Let's say that for this value of the disorder strength, H equal to 0.5, the system is in an ergodic phase or extended phase or thermalizing phase also. We compute and we compare with this distribution. Lea already said something during the morning. If this histogram conforms with the prediction for the Wigner-Surmise or Wigner-Dyson distribution, then we say that the system is in a chaotic phase. In this case, we see that there is a great correspondence, a very good correspondence with the Wigner-Dyson distribution, in which increase the value of the disorder strength, then the distribution is not Poisson, it's not Wigner-Dyson. And if we increase larger the value of H, the distribution conforms very well with the exponential distribution, which is a case for when the system is not chaotic. In this case, when the system is in a localized phase. Then we have this transition from Wigner-Dyson to Poisson. These results are for L16, 16 particles, but at half filling, I mean in the subspace with zero total magnetization in the Z direction. So the other thing is the dynamics for the different observables that I present you. I consider this model with uncorrelated disorder with delta equal to 1. Here is, for example, the survival probability for 3 different values of H, again in the ergodic phase, in the intermediate phase, let's say, and this in the localized phase, and this represented by these curves. Here, what I'm presenting in each panel is, for example, different curves for different disorder realizations. If we have a disorder, then we need to make an average of different disorder realization, because you can see that there are sample-to-sample fluctuations. Then these soft curves represent individual samples for different values of the disorder strength, and this solid curve represent the average over different initial states that we consider initial states of this kind. And the particularity of these initial states is that they are close to the middle of the spectrum. I mean energy close to zero. And we make this average over different disorder realization of different initial states. And we can see how Lea already talked about this behavior, this transient behavior, which is Gaussian. Then we have a kind of overload decay. Then we have the correlation hole and then the saturation. And as we increase the disorder strength, the correlation hole disappears. We have a quick saturation, and the system is localized. I mean, localization is reflected into the dynamics of the system, not only in this quantity, the survival probability, but also in the spectral form factor, which is K, with time. Then we see this again, the ramp. And then when the disorder strength is large enough, the ramp disappears in this case. And we have similar behavior for different quantities. This is the spin autocorrelation function, very similar to the survival probability with this kind of overload decay or slow decay with time, then the correlation hole, the saturation, and then again for a strong disorder strength, the quick saturation of this quantity. This is the connected correlation, spin-spin correlation function, which is start at 0 because the initial state is a product state. That then at time equal to 0, it starts at 0, and then correlations increase as we increase the time for different disorder strengths again. So this is the general picture that we have for the dynamics for different observables. Here I am marking this green line, which is only to represent that we are going to work at large times. I mean, we are going to compute different quantities once we are in this region in the evolution. I mean, once we are in saturation. So since we are interested in the probability distribution function of these observables at large time, we have two different approaches to obtain these probability distribution functions. One is, for example, we have a disorder system. We can fix a time, a specific time, and we can compute the distribution function of these observables with respect to different samples, I mean, over an ensemble. Then we can compute this distribution function. Or the other approach is to take a time window represented by these lines for a single realization of the dynamics and to compute the distribution function of this observable. So the question that I have here, or that we have here, is that if there are implications on the mean localization. In other words, if we can distinguish an extended phase or a localized phase in terms of the dynamics, in particular in terms of the probability distribution function of this generic observables, or this specific instead of generic specific observables. Here is what I have. I repeat here the level space distribution just to have the comparison. We have the extended phase, the intermediate phase, and the localized phase. And this is the probability distribution function of the values of the survival probability considering this approach, because I'm going to focus in this approach. If we do this, when the system is ergodic, we have similar equivalent results in these two approaches. When the system is in the localized phase, we have different phases, different distribution functions, but I'm going to talk about this a little bit later. So again, here this is the distribution function of the survival probability. We see that this is exponential in the extended phase when we have the Wigner-Dyson distribution for the energy eigenvalues. In the intermediate phase, this distribution function doesn't conform with the exponential distribution, and a large, let's say, a strong disorder strength, 6 in the localized phase, the distribution is not more exponential. It's a different shape. I don't know what is this shape, but this is specific for any initial state and for any disorder strength if we go beyond this value. So we have an explanation why we expect this exponential. I mean, why this distribution should be exponential in this phase. We depart from this survival amplitude, which is the square root of the survival probability. We can expand this, expand this expression in terms of these two variables defined in this way. This and this is y, this is x. And if the central limit holds, then the distribution, I mean, if this quantity is it has a Gaussian distribution, and this quantity has also a Gaussian distribution, then one can show that the absolute value of this complex number is an exponential distribution. It's a Gaussian distribution, sorry. So this is this is not a Gaussian distribution. This is a Weibull distribution, a specific case of Rayleigh distribution. So, but this happens only if the central limit theorem holds. I mean, this means that this x and this y behave like independent statistical random variables. Then if they behave as independent statistical random variables, then the distribution of x and the distribution of y can be approximated by a Gaussian distribution. So if we have this Gaussian distribution, the distribution of this is only a transformation, is this Rayleigh distribution. So for the case of the survival probability, we take the square of this, we have the transformation, and we obtain an exponential. So this is why we have this exponential in the late time distribution function of the, unless for this survival probability. So for the spectral form factor, for example, if you remember the definition of the spectral form factor, where is this? This is only the eigenvalues are involved in the spectral form factor. Then we have always, for this spectral form factor, for the distribution of the spectral form factor, we have always, for any disorder strength, we have always an exponential. This means that this behavior, the eigenvalues behave as uncorrelated random numbers. Statistically, I mean, meaning as uncorrelated random numbers, because here in the spectral form factor, only the eigenvalues are involved, energy eigenvalues, right? The components are not involved here. So this means that correlations between components of the initial state must be relevant. I mean, relevant for this analysis. No? If there are components, we are not going to, if the components of the initial state contain some kind of correlation, then we are not going to have here the exponential distribution as we see here in the survival probability. Then, and we check this. I mean, we define, this is a well-known quantity, which is the Pearson correlation function. For example, this is a correlation function. This is a measure of the correlations or autocorrelations between these values x at lag k. This is the lag. Then n is here should be the same n. N is the dimension of the Hilbert space of the subspace. This is the variance of this x, and this is the mean value. This mi is the mean value of this random variable. So if this correlation function is 0, then this means that there are no correlations. If this correlation function is different from 0, then we have correlations. Here we check, for example, these correlation functions for the eigenvalues for the initial state components, and this for the X and the Y that we defined in previous slides. So you can see here that for any disordered strength, you have that the correlation function is 0 around this, I mean inside this confidence interval, which is of 95%. So this means that the eigenvalues behave as uncorrelated random numbers in this case, which confirms what we see here. We have always the exponential, so this means that the central limit theorem holds for this case for the spectral form factor. But if we consider the correlation function for the initial state components, we can see that for a small disordered strength, I mean in the extended phase, the components are uncorrelated inside this confidence interval. But assume we are in this regime or in this other regime, we have correlations between the initial state components. So this is what I mean. This is what results in this kind of distributions that don't conform with the exponential distribution. I mean, this makes that the central limit doesn't hold. Sorry. Yeah. Because this is some overlap, right? Yeah. Yeah, this is an overlap. This only to go. This is which one? Previous slide. Previous slide. This one. This one. Yeah. SP is an overlap. Yeah, SP. Yeah, is the survival probability. Where we have numbers larger than 1. Here. Yeah. This is the distribution, and this is, yeah, we make a kind of rescaling of this quantity, but I don't remember this in this moment which kind of rescaling. We have the paper, but these details I don't remember. And yeah. Then this bimodal structure, is that something that can be explained by local integral motion? Yeah, this is a good question, and this is a question that I made myself, but I don't know how to relate this bimodal distribution function. But this is interesting. This is not the first time that I asked this question. Okay, but interesting. Yeah. Okay. So okay. So again, let's say in consequence, if we have this kind of correlations between the initial state components, autocorrelations, then these correlations are reflected also in this X and in this Y. For H small, we don't have correlations, and this is why the central limit holds, and why we have the exponential distribution, for example, for the survival probability. And for a strong disordered strength, in this less in this regime and in this other regime, we have correlations. But these correlations are, I mean, transferred from these initial components of the initial state into these variables. Then for the observables, for example, we have again here this bimodal distribution, but here we don't have this bimodal distribution. Then for a small disordered strength, we have this Gaussian distribution, very well behaved Gaussian distribution. If we increase the disordered strength, the distribution is different from the Gaussian, and we go up to a stronger disordered strength, the distribution is not more Gaussian. Something similar happens with the connected autocorrelation function. The distribution is Gaussian for a small disordered strength and not Gaussian for large disordered strength. So we have a Gaussian for the observables. I mean, this specific observables, they have this universal Gaussian probability distribution function at late times in the thermal region. When the system is in this localized phase, the shape of the distribution is very specific. It's not universal. It depends on the initial state, depends on the observable. But when the system is in the ergodic phase, the distribution is universal for this kind of observables, and in particular for the survival probability is also exponential. So what I'm going to present to you now is this other work also. We work in this model, the same model, but now these HK are again random numbers in this support. H again is the disordered strength, but now we introduce correlations between these random numbers. And we introduce this kind of correlations in terms of this f, which is a cumulative distribution function of this random number, which this random number is a sum of a sum of random numbers with a uniform distribution. And C is a parameter which is useful to control, to tune the level of correlations within the random numbers. So what we know is that this kind of correlation is exponential. For example, K is the lag. And in all cases, for example, C2, which is, let's say, is kind of small, because this is the prescription. If we have C close to 0, then we have weak correlations between these elements. And if C grows larger, then the degree of correlations increases. Then this is an example of how these correlations behave with respect to the lag. For example, this is for a small C. These correlations decay as we increase the lag. For the other values of C, I mean, we have stronger correlations. They decay slower than in this case. So now we are going to analyze how the dynamics behaves, and some static properties also behaves with the level of correlations between these random numbers. And here's what I present you now. In this case, I present this ratio of the ratio between the level spacings, consecutive level spacings, this average with this R defined in this way in terms of the energy eigenvalues of the system. And here I present you the results with respect to the degree of correlations between the random numbers. Remember that small c is absence of correlations, weak correlations, and large c is strong, means strong correlations. So we can see that in this case for H.5, which is in the ergodic phase, for some values of C, this behavior remains. I mean, the prescription, this value is the prediction of this R for the extended phase that conforms with the GOE prediction, Gaussian orthogonal ensemble of random matrices, which is this value. And this blue is for the prediction, the theoretical prediction for the localized phase, which this is for Poisson-like distribution. Then we see that for a small disordered strength, as we increase this value of the degree of the correlations, this R remains at GOE, but as soon as this goes to larger than 1, this decrease, passing this prescription for Poisson. For the other values of H, for example, H3.75 and 6, we can see that first we start here in the localized phase, I mean Poisson-like distribution or Poisson-like statistics. Then we increase enough the value of C, and then the system goes, unless the statistics of the energy eigenvalues goes to the prediction for GOE. So we have a kind of destruction, unless an indication in terms of these statistics, a destruction of the many-body localization due to these correlations between the random numbers. This is reflected also not only in energy eigenvalues statistics, but also in the structure of the eigenstates of the system. We can study this structure of the eigenstates of the system in terms of the inverse participation ratio. These are the components. If the inverse participation ratio is small, then this means that the eigenstates are extended. I mean, many of the basis states participate in the structure of the eigenstates. No? So you can see here, for example, this is for H.5. We start, the states are extended very close to the prediction for GOE, which is this one. This is the dimension of the space in which we work. And we increase the values of C, and the eigenstates remain extended in the side. Let's say this is the basis, a specific basis, which is formed by the eigenstates of the spin half operator in the C direction. Yeah.
Why the red one goes down at light C, but not the blue and green?
The red one. Yeah, this means that the correlations are strong enough, and we go beyond the Poisson-like statistics, and maybe some degeneracies appear there and we have a different shape, not the Poisson one. For this, we have always, we can see, and I have an analysis here, I have this system size, but I have an analysis for different system size, and we can see that this remains in the GOE prediction. Always, it doesn't go. Yeah, no, this is something that I don't understand why this happens for this case, no? But for sure this remains in this GOE prediction. Yeah, so for the other values of H, for example, 3.75 and similar to 6, you can see we start here, the states are localized. Yeah,
so just a quick question about how you kind of recover this Poisson statistics. So this is for the XXZ model with basically on-site disorder, right?
Right.
So in the extremely correlated case, I would expect that basically all of the H's are the same and you recover an integrable model. So I was also wondering, what would happen if instead of having like an integrable model with this disorder, you get a chaotic model and add disorder? Because I was thinking that maybe as you pull up, as you increase C, maybe it's just the integrability of the model that you're recovering rather than...
Yeah, when you have the chaotic model.
Yeah.
Yeah, but this is what happens here, right? I mean, this is for this value, the red one is for a chaotic model. And then you increase the value of C and you recover this, this Poisson-like distribution.
But so in the extreme limit where basically these are all, maybe I'm just misunderstanding the correlation, but I expect like in the limit where these extremely correlate, where essentially these are all the same, you recover Poisson statistics because the model is integrable.
Yeah.
Yeah.
Yeah, right.
Okay.
Yeah. Yeah, yes. Yeah. Okay. So, and we increase the level of correlations, we go to the prediction for GOE. So again, for this case, in the strong disorder strength, or let's say for these values of disorder strength, which is supposed to be in the localized phase, for the any eigenvalues, we have this GOE prediction, kind of destruction of the many localized phase, and this is reflected also in the eigenstates of the system. So this is written here, but I'm going to move to the next slide. Here we have the dependence on system size. For example, I present here the average of this R with respect to C for different system sizes. You can see from 12 to 18. And you can see how this goes, for example, for GOE, and how this extension of the GOE prediction is increasing as we increase the system size. This is a kind of indication, let's say, a finite size indication that as we increase the system size, this will extend even more if we increase the system size more. No, it's not a finite size effect, let's say.
We see that it goes downwards, even at largest. On the previous slide, it was not there just because the interval of C was not bigger.
In which, in this one?
Statistics on the left, blue and green.
Yes.
They go down, right?
No, green. Let me see. Yeah, maybe in this case. Yeah. Okay. Yeah. The interval is different. No, but you can see that actually in this case, for example, the extension of this region is increasing as you increase the system size, right? Yeah, both of them. No, both of them. So this meaning that if you increase even more the system size, maybe in the thermodynamic limit, this will remain, no, for larger values of C correlations. So for this analysis for the inverse participation ratio for the structure of the eigenstates, we see that for H.5, for different system sizes, the states seem to they are extended. No? I mean, they don't go to 1 and so on. They remain around this prediction for GOE. But in the other case for H3.75, H6, we see for different system sizes that the curves collapse for any system size in this region. They remain in the GOE predictions for any disorder strength. So this meaning that it's a kind of suppression of many localization due to this strong degree of correlations between the disorder potential. Yeah, go ahead.
Thanks. Yeah. So it's very interesting. I have one question. So here you're looking at this average R value. Do you have some idea what the distribution actually looks like in these different regimes? Because that would also kind of tell you why this is dropping so low or where this is coming from.
Do you mean a distribution for the IPR?
No, not for the IPR, for the R value. So in the top panel.
For the R distribution? In this case, no,
Yeah.
I'm not looking for a distribution here in this case.
Yes.
Yeah, I never saw the distribution for this.
Okay.
No, but I think we have a peak, something like that, close to zero. For example, if we study the level spacing distribution.
Okay, thanks.
Okay. Yeah. You can go. Okay. So I think I'm close to finish. Let me see what is this. Okay. So now for the dynamics, I have results for different observables also. But this is an example, the survival probability under correlated disorder. This is the definition of the survival probability. We have here strong correlations. We have weaker correlation as we decrease the value of C. And we see here, for example, for strong correlations, 3 different values of H again, 0.5, 3.75, 6. And we can see, for example, for these values, 3.75 and 6, that we have something very similar to the ergodic phase. I mean, we have this generic behavior for this kind of models in the chaotic phase. But the blue and the green is supposed to be in the localized phase, and the only thing that we have is this kind of correlations, strong correlations between the amplitudes of the disorder potential. No? So we have the correlation hole, and we have the saturation. Then as we decrease the value of the correlations, the degree of the correlations, we recover the usual behavior, which is similar to here, but only for the small disorder strength. H.5. For the other cases, we recover the usual localization, quick decay, and then quick saturation, also a large saturation value, and so on. So again, we see in terms of the dynamics that the many-volume localization can be suppressed by this, the introduction of these correlations between the random potentials. Okay, so in summary, this is my summary. We study the probability distribution functions at late times of some specific observables. In the ergodic phase, we see that the central limit theory holds, and then the probability distribution function, the survival probability and spectral form factor are exponential. The probability distribution function of the correlation functions are Gaussians, and in the many localization phase, the probability distribution functions are not universal. For the autocorrelated disorder, at the ergodic phase, the level repulsion and structure of eigenstates are robust against the correlated disorder. But beyond this ergodic phase, and for strong correlations, the level repulsion and extended states are achieved. Dynamics can be also controlled by this autocorrelated disorder. We see that for a small correlation between the disorder, we have a GOE-like behavior. For a strong disorder, strong correlations, we have also a GOE-like behavior of the dynamics when the disorder strength is large enough. So I would like to thank you for your attention, and that's it for my part.
Thanks a lot. More questions? Okay.
Maybe first this clarification question, because I didn't get it maybe very quickly. So can you remind us what is this autocorrelated disorder once again? So it was defined via some cumulative distribution function, but I didn't get it. Can you explain it?
This,
yeah, this HK.
Yeah.
What is this F?
This F is the cumulative distribution function of this X, which is a random number. And you form this random number as a sum of two normal random numbers with certain distribution. I mean, I'm going to write here because I can, maybe with these letters. You have this one uniform random number with mean 0 and variance 1, and another random number with mean 0 and 1 over C variance. 1 over C, I don't remember.
Okay.
So you sum these two random numbers, and then you compute the cumulative distribution function, and you use that prescription to form this this correlated random number.
And xk is another random number.
K,
XK.
K is the last.
Xk.
I mean, yeah, you have two random. Let's say you have one set of random numbers.
Yes.
Then you shift a little bit, and this shift is the lag. No? I mean, it's a kind of autocorrelation function between autocorrelation function. You have the random numbers that you measure, in some sense, the correlation that they have.
Maybe can you explain in simple words what is the physical meaning behind that? What do you like to achieve with this?
To achieve with the correlation?
Yeah, with these correlations, because like you can invent many kinds of correlations. What would you like to achieve with these concrete ones?
This was a curiosity, because sometimes when you have, for example, the one-dimensional Anderson model, you know that for any finite, any degree of disorder strength can localize, exponentially localize, and it has been shown that for this one-dimensional model, if you introduce some kind of correlations, you can break this localization.
But depending on correlations, you can either enhance localization or make it delocalized. It will depend on correlations.
Yeah. Depends on the kind of correlation. With this kind of correlation, we can to achieve the kind of destruction of the many-ball localization phase. No? And this is what we achieve here in this case. This is what I'm showing here.
Okay, thank you.
Some more?
Yeah, essentially, I have similar question than Ivan. So uncorrelated is just in one way, and correlated is in different ways.
Yeah, it depends.
So do you expect these results to be like general for
for any kind of correlations? I don't know. For example, you have the Aubrey-André model, which is a kind of correlation. I don't know what kind of correlation is that, but you have a kind of correlation there, and you don't have this behavior because you increase the value of the amplitude, and you have a transition from extended to localized, and you never see this, even if this is correlation. No? But I don't know how in the Aubrey-André model, for example, you can tune the degree of correlations. But I don't know if this is for every kind of correlation. This is for this specific kind of correlation. But this is a good question.
More? Okay, if not, we can close the session.
Okay.
It's confirmed tomorrow. First talk will be at the first floor. Okay.